Lecture 4.3, Heat Engines, Energy Transfer Diagrams, and Efficiencies. What is a heat engine? Internal combustion engines are the most common form of heat engines. They're also used in boats, ships, airplanes, and trains. They're named as such because the fuel is ignited in order to do work inside the engine. So if I was to write this differently, I would probably say it's a device that converts heat into work. It takes heat from a hot reservoir then does some work in a combustion engine, like move a piston in your car, and finally transfers heat exhaust into a cold reservoir. So let's do a visual aid, okay? So just to write down in a picture what I just showed you here is I would say that here's a visual aid. And this is actually called an energy transfer diagram. So here's what I see. I have a hot reservoir. Okay, here's my hot reservoir. And you got to pay attention to the width. So I'm going to be careful with the width. So I'm going to look at the width. So I'm going to take heat from the hot, okay? And so here's my hot reservoir. And so I would say that this is the hot reservoir. And it has a temperature of T hot. Now what happens here is that I'm going to take heat from this, and what a part of it is going to go in this direction. And so the way you do that is that you have an engine. So if I look at my engine, it's going to look something like this. And so what you're seeing here is that the width of this guy is now being transferred into two places here. So if I look at my heat, all of my heat from the hot reservoir is now being divided into two places. This is the direction of Q hot. Part of it is then used for work. And it turns out that this is the output work. And then part of it is then ejected into the cold reservoir. And of course, the cold reservoir has a lower temperature. So then I would say that this is now our cold reservoir. And it has a temperature T cold. So then Q cold is coming out of the engine. And so this guy right here is the actual engine. So it's a theoretical picture, but it's a good theoretical picture because it shows you exactly what you're looking at. Now, what you're seeing here, all heat engines have the same two requirements. All heat engines require two pieces or two parts, whatever. So the first thing here is that their operating cycle must be repeatable. It has to repeat itself over and over again. Think about your car. Those pistons have to move up and down again and again and again. So the process, we then say that we have a cyclic process. So what does it mean by a cyclic process? And you're going to see that we're going to have a change in internal energy here. I mean, a change in notation. So if I look at that, so from the first law, we know that if I look at the internal energy over a full cycle, that must be equal to 0. And up to this point, we've been saying that this is Q plus work. This is the work of the gas, right? We added a minus sign. So once again, this is the work done by the gas. We are not interested in the gas anymore. We're talking about work that is being pulled out of the piston or being pulled out of the engine. So we have a change in notation. Okay, here's our change in notation. So now what I'm saying here is that this guy tells me that now we're going to change notation. And we then say that, by the way, I should have put net here right there. And then it's going to be Q net. And now what we're going to do here is that, look what we're going to do. We're going to put a minus sign and we're going to change how we write work. We're going to say that the work now is the output work. So instead of talking about the work by the gas, in this situation, we're going to say here is that this is the work taken, maybe I should write that big, taken out of the system. So then here's what we're saying here. That means that if I rewrite this whole thing, this then tells us this here, that Q net is now equal to plus the work out of that system. But Q net is also Q hot minus Q cold. So it turns out that this becomes the most important relationship when starting to look at engines. And then picture-wise, it makes sense. For a cycle, there is no internal energy, there's no change, so we don't even have to include it. But picture-wise, I see that, let's say, if I do this amount of heating from the hot reservoir, then I have to eject some heat out of the system in order to get back to its initial state. Then the difference between these two tells us that we just did this amount of work out. If we didn't write it this way, we would have a negative sign, and that's a little bit harder to interpret. So once again, this is the heat added, and this is the heat that was ejected. Okay, so that's the first thing that has to happen. The second thing, which I kind of already stated here, it must include water to dump the heat exhaust. So if you look at your car, so as an example here, in your car, you find here is that your car ejects heat from the exhaust pipe as well as dump heat into your car's radiator. So, and there's part of it is also air cooled. So there's a lot that's going on here. But you cannot have an engine without those two pieces. Okay, so here we go. How does entropy come into engineering thermodynamics? Well, it turns out that I have to really break this piece a couple of ways. The first thing that I would say here is that the first law does not make any distinction between heating and working. In fact, we already said here that for a cycle, we know that the internal energy is zero, but then we have the net heat plus the negative work out, which implies here is that the net heat must be the work out. In other words, I can't tell the difference between those two. However, the second law does differentiate between the two. And so here is where we start to really get into the details here. So a heat engine that operates in a cycle and not solely take energy from the hot reservoir, QH, and put out an equal amount of work. In other words, Q hot cannot equal the work out. Okay, it cannot do that. This engine, and remember what we said about what kind of engine. It has to what? It has to operate on a cycle. Okay, it has to operate on a cycle. This engine cannot be constructed and we'll get to those details here in a moment. So if, let's say that you could do this, if this was the case, the engine would be 100% efficient, which tells us that it's impossible by the law of the second law, it's impossible to do. That is, every engine must eject / transfer unused heat into the cold reservoir. To be cyclic. And as soon as we go through the details, you'll see what I mean. So picture-wise, what am I saying here? Since I drew the diagram already, I'm going to steal this diagram right here. Okay, so right away, the second law shows us this here. So if I do this, I'm going to modify this picture. So if I look at this picture, I'm going to come in and I'm going to modify it to explain what it is that I'm talking about. So I can't eject anything into the cold reservoir. So in this case, what we're saying here is that Q cold is equal to 0. Now, if I come back and I look at the details, then that means I cannot do this here. I cannot take all of my heat and put it into work. If you did that, then you'll see here is that you're seeing that they're not the same diameter, but they should be. So if you had this situation, then this implies here that this would be 100% efficient heat engine but it makes no sense. It's not possible. So this cycle here is not a possibility. So here's what we're going to do now. So now let's go into the details. The second law shows us, one, how a practical engine transforms, and here's the important piece, right? Internal energy. But in this case, it's also the heat that we're extracting. And you got to remember here that this tells us here that this is really K micro. We're transferring K micro from one location to another into work. Again, remember, heating is the workless transfer of energy. And then what we're going to find here is that now it tells us what limitations or restrictions on these energy transformations. And the way we'll talk about the second law here is that we're then going to go into the details of energy transfer diagrams and entropy. So we're going to use pictures to really show you what are the requirements here. And here we go. So these diagrams will show how entropy limits the kinds of possible engines. So let's talk about language here before we get into those details. So what we need to do is we really need to talk about reservoirs. So hot and cold reservoirs in thermal are idealized objects. Sort of like a massless spring or string, a frictionless surface. They're idealized objects. So if heat is transferred out of the hot reservoir. I could have said heat transferred into the cold reservoir. Its energy slash temperature does not change. Now we could make a reservoir, a very, very good one, just by the following analogy here. So if I give you an analogy, they can't change energy, internal energy, and they can't change the temperature. So let's say that the reservoir that we're talking is about the water in the ocean. So if one dumps a gallon of boiling water into the ocean, its internal energy slash temperature does not change in a measurable way. We can theoretically think that it happens, but when you go to measure the difference, you're not going to see that difference. It's very, very sensitive to think that nothing would change about that. So when we talk about the hot and the cold reservoir, we're saying that no matter how much heat you transfer out, or how many you transfer into the cold reservoir, the temperature does not change. So now let's look at possible slash impossible processes. And let's list them. So the first one I want to look at is I want to say heat can flow, transfer from a hot to a cold reservoir. In other words, Q hot will transfer energy to Q low. Why? Q hot has right, when we start comparing like we did before, it's always going to move towards equilibrium. Why? It's the most probable state. So picture-wise, what am I seeing here? I could imagine that I have a system that looks something like this. One of these blocks is hot, the other one is cold. So this hot and this cold tells me that I'm going to have heat transfer in this direction right here. Now, how do I set this up as a process on a diagram? Well, I could imagine that I take a copper pipe, right? There's a copper pipe right in here. And what I'm going to do here is that on one end, I'm going to have a fire over here. And at this other end, I'm going to place ice. So here, I'm going to have a fire. And then over here, I'm going to have ice. So this represents the hot reservoir. And this represents the cold reservoir. In other words, I have a hot temperature here, and I have a cold temperature here. So when I look at the transfer of heat, it's going to move in this direction. And by the way, I think I said it, I may not. I'm going to say that this is a copper pipe. So what does this look like on the transfer diagram? Well, I have to have my hot reservoir, and I have to have my cold reservoir. And so what this is telling me is that as I go down, I can, you know what? I should have done this first. Let me over to the right here. The first law states that the internal energy for any cycle has to be the net, work something like this. Not for a cycle. I'm just going to say it's the heat times the work here. But remember, this guy, when I'm taking heat, there is no work done here. That's zero. So in this case, this heat that changes the internal energy has to be the difference between the two ends of the rod. So this tells me then that Q net has to be Q hot minus Q cold, which then tells us that then Q hot must equal Q cold. Right? So that's what we're saying right here. So what does it look like on a transfer diagram? That means here that all of the heat, and by the way, I should be drawing my system right here. The purple here represents the copper rod. So then that means that the heat coming out of the hot reservoir all flows into the cold reservoir coming out. So I didn't take this all the way down to there. And so what you're seeing here is that you're seeing this. Here's my hot reservoir. Here's my cold reservoir. And we're seeing the transfer of heat coming in this direction here. So that's a possible process. Now, the second law states that heat transfer always occurs to the most probable outcome. And that's the one with the increasing change in internal energy. However, the second law forbids the opposite transfer. And the opposite transfer is that if I look at this guy, if I look at my transfer energy here, that when I look at this here, and I look at the transfer process, that energy cannot move from the cold reservoir, T cold, to T hot. right? It can't do that because it's a low probable outcome because delta S is negative. The entropy is negative. So this diagram is not possible. That's what I mean by the second law does not allow this. Again, first law, what does it say? Well, it says that it allows, well, Q hot, no, it allows Q cold to move towards Q hot. It can't tell the difference. But the second law says just the opposite. It says that it does not allow a decrease in entropy. Now, let's look at another of the diagrams too. This one here is that we could say here is that work can be completely converted into cold heat. And you'll see what I mean by that. I really mean heat. So what do I mean about that? So as an example, let's look at a book sliding across a frictional surface. So if I look at this guy, this right here represents my frictional surface, right? So this guy here is my frictional surface. So now if I have my book here that I push and I slide across this floor, then what's going to happen here, right? You're probably going crazy in this course, so I'll write physics. Then what's going to happen here is that I am going to do work. And when I do work, what do? I change the energy of the system. So what happens? There's heating between the ground and the book, right? So the book now gets hot down here at the bottom, as well as the surface. And then you're seeing here that heat goes up into the environment. So what I'm saying here is that the work is transformed into heating of the cold reservoir. So then my picture has to look something like this. So here, there was no heat put into the system. So when I'm thinking about my reservoir, my hot reservoir is not really part of the picture, so it's not attached. So this is our hot reservoir. It plays no part. But now what you're seeing here is that I did mechanical work. And as I do mechanical work, I can then take that mechanical work and completely convert it into heat ejected into the cold reservoir. So here's my cold reservoir. And then there's the transfer of energy. And then this right here is the heat. Or excuse me, the work. So now I have work. And what's the work doing? It's taking energy and it's moving it into the cold reservoir. So what you're seeing here is that this process is 100% efficient, which means the energy supplied by working is completely transferred into heat QC. 3, heat into work. This transformation is not so simple. The energy supplied by working, oops, that's not where I want. I'm repeating what I just said here. This is not so simple, and the second law plays a large role. As I've already stated, practical devices must be cyclic. In other words, a device that transfers heat into work must return to its initial state at the end of the process. And this is what makes it complicated right here. So when you say cyclic, in some shape or form, I gotta get back to this thing. So I'm going to show you a more of an educational cycle involving a nuclear power plant. And then right here, this is called a Batron cycle, and it's more educational than practical. But what you're seeing here is that this is a nuclear power plant. But I could have done the same thing with the combustion engine. I could have done the exact same thing with the diesel engine. So what you're seeing here is that there's 7 steps. There's really 8 steps. And so you can see here is that if I look at this thing, here's what I'm seeing here. This guy right here is 1. So I'm going to look at 1, 2, 3 right away. Okay, so this is number 1, number 2, and number 3. So what you find here is that the way this power plant works is it has a water pump. Okay, so this guy is a pump. So when I look at the process from 1 to 2 to 3, what you're seeing here is that 1, 2, 3, you feed water using pumps. And this here is the cold water. In fact, it turns out to be the cold water reservoirs, as you'll see. Now, when you look at this thing here, and by the way, what happens here is that now you're going to we're going to go in and we're going to look at process 4 and 5. So here's 4 and here's 5. You now pump it into the boiler. So you're going to, so now you have the boiler that boils water under high pressure. And as a consequence, you're going to see here is it's going to create steam. So how is the boiler acting? So you're seeing this because this is a nuclear reactor. You're seeing these yellowish rods. These are what are called the nuclear rods, where you have nuclear interactions that then transfer kinetic energy to the water. And in this process, it now becomes steam. So now that I have steam, then you go through the process of 5, 6, and 7. So now you have pressurized steam that is shot at a turbine or turbine blades. So in this situation, you're now seeing here that I'm going from 5, 6, and 7 here. So now what you're finding here, when it hits these turbines, it makes them spin. So it spins and does work. Okay, so now what you find here is that now you're spinning. What is left now? What is left? By the way, this right here, I probably should have said this. This is where I go through a system where I get pressurized steam. Okay, and then right here, you have a turbine. And if you had physics 4B, I now have a spinning magnet. Then from Faraday's law, it produces voltage and current. So now, here's the important piece here. And here's where I now get to 7 and 1. Question. To be cyclic, what must one do with the left over exhaust, leftover hot exhaust steam. You have to cool it. So one must dump the unused hot steam into a cold reservoir. So what's the hot reservoir? What's the cold reservoir? The hot reservoir is this guy right here. That's where the steam, that's where all the heat is coming from. And if you look at the cold reservoir, it's the ocean water here in these pipes. That's the cold reservoir. So what you're seeing here is that heat is being dumped into the cold reservoir, which tells us that QC is not zero and can never be zero if you want a cyclic process. So now, if I look at this in terms of an energy diagram, you know what? I think I'm going to go back and steal this guy. See, I already have this guy. So I'm going to copy this. So right away, what this is telling me, just by looking at this diagram, you could see why you can never have 100% efficient. In order to be cyclic, you have to dump the water into the you have to dump the exhaust heat into the cold reservoir. So now if I just use the previous diagrams, I have this. So here we go. Any possible heat engine must eject heat into the cold reservoir. So now let's look at the details, the mathematical details, right? If you had the other one, no, as we said, no heat engine can be 100% efficient. That's cyclic. So now, here we go. So now let's look at the mathematical details of heat engines. And what we have to do here is one of the key things is we need to talk about efficiencies. And here's what we know. The first law says, we've already said this multiple times. The first law tells us that the change in internal energy for a cycle is zero, which then means that we have Q net, now look what I'm writing, minus Q out. Remember, we changed notation. So then that implies here that Q net is equal to Q hot minus Q cold, and that's going to equal to plus work out. Second of all, to measure the performance of a heat engine, one calculates its thermal efficiency. Now, here's the problem with thermal efficiency. There's two notations. I like the symbol epsilon because that's the most common one. There's another one that has eta that's also common. So I'm going to use epsilon. Okay, so now that we have that, here's what we're going to look at. So what we say here is that real engines are irreversible. Cycles. Whereas Carnot engines are reversible cycles. And this is what it says here. If I have a engine efficiency, a real engine efficiency, let me write this real, that this is a real engine. Look how I'm going to write this. I'm going to redefine this as engine. So if I talk about a real engine, if this calculation shows that the efficiency of a Carnot engine is greater than the efficiency of a Carnot, then it tells us that this is an impossible engine. And for a period of time, I was an evaluator at NSF, and the people who did thermodynamics and specifically engines, they always said that if you had a real engine that had a higher efficiency than a Carnot, you violated the second law because somewhere you are transferring heat from the cold reservoir to the hot reservoir. And all they had to do was just have the patience to find that. And so it's an impossible engine because it violates the second law. If the Carnot efficiency is greater than the engine efficiency, then this tells us that it's a possible engine. That's the difference right there. And like I said before, it's not simple, but if you were to really analyze these carefully, they say that almost inevitably the way it violates is because now one transfers heat from Q cold to Q hot. And we know that violates entropy without any doubt. So let's define the efficiencies now. So now let's define the efficiencies. So if I have a real engine, I should have just written engine. So here we go. So I'm going to go I'm going to abbreviate engine by NEG. It's not like I'm saving a lot, but I'm saving some. This, by definition, is the how much work did you get out for how much energy you put in. There's a lot of ways to say this, but what you had to pay, how much did you pay to heat up that water versus what you get. In this case, how much electrical energy was put out. So there's another way to write this. Now remember, we can also write this, or we can write the work out in Q hot. Well, this is also Q hot minus Q cold divided by Q hot, which is then 1 minus Q cold over Q hot. So in other words, the engine efficiency can either be written as the work out versus Q hot, or 1 minus Q cold over Q hot. So which one to use, turns out in general, it doesn't matter. So if it's easier to calculate the work than the cold, heat, the heat ejected from the system, then that's the way to go. So you really have to compare which is easiest to calculate. Is it the work out versus the work cold? If the work out is easiest to calculate, then use work out divided by Q hot. If the heat ejected by the system, if that's easier to calculate, then use the second version. And then finally, we now have the Carnot efficiency here. So the second law states the Carnot, the reversible Carnot engine is the most efficient engine between the hot and cold temperature reservoirs. And as I already said here, nothing is more efficient than a Carnot engine. So therefore, the Carnot engine sets the upper limits on efficiency. And here is the thing here. So if I have a Carnot engine, it still follows this guy right here. It's still between these, hot and cold reservoirs. But then here's what you can derive here. And what you can derive here, okay, that means one can derive that it actually doesn't depend on the heat. It only depends on the temperatures of those reservoirs. So what you should do here, you should only focus on temperatures, not the heatings between the two.